to introduce our resource person for today's session, Professor Subhash C. Ray, sir. Sir is presently working in the University of Connecticut, USA. Sir is presently working in the university, and Sir is an alumni of the very prestigious Indian Institute of Management, Kolkata. Sir has completed his PhD in economics in the year 1981 from the University of California, which is located in Santa Barbara, USA. Sir has over 40 years of professional experience in the field of education and has published over 65 research papers. His principal area of research is non-parametric measurement of productivity and efficiency using data envelopment analysis. Professor Subhash C. Ray sir has written a reference textbook which was published in the year 2004 under Cambridge University Press. The name of the reference textbook was Data Envelopment Analysis, Theory and Techniques for Economics and Operations Research. He is an associate editor of the Journal of Productivity Analysis. Sir has served as a guest editor for the special issues of Journal of Productivity Analysis and Indian Economic Review. Professor Subhash C. Ray was a member of the editorial board of the Indian Economic Review. He has lectured and conducted workshops on data envelopment analysis in different countries, including India, China, Korea, England, Brazil, Peru, Malaysia, and Turkey, among others. He received the prestigious William W. Copper Lifetime Contribution Award from the International DEO Society in the year 2016. Today, Sir would be talking about productivity, efficiency and data and envelopment analysis, efficiency measurement under variable returns to scale. Sir would also be talking about the theories and hands-on computation on Excel. We're fortunate enough to have Professor Subhash C. Ray, sir, with us as our research person in this online 2-week-long faculty development program on research methodology and applied econometrics for social sciences organized by the Department of Business Administration, Assam University, Silchar, a central university, in collaboration with Vidyasagar University, West Bengal. Over to our co-convener of the program, Dr. Sravanti Maiti Madam. Thank you, everyone.
Thank you, everyone. Thank you, everyone, and special thanks to Kollan. Professor Ray, please, you start.
Well, thank you, Sravanti, and thank you. You can hear me?
Yes, sir. Very loud and clear.
Okay, thank you. I don't want to be too loud, but this is morning here, you know, it's a very bright, sunny Friday morning. So you can't be too muted in a day like this. So,
Sir, I'm sorry, I'm interrupting you. I have a request. At the end of the session tomorrow, I request you that if you could able to recite your body poem, we will be very delighted.
What's that?
Your body poem.
Okay, maybe maybe tomorrow or whatever.
Yes, sir.
So
I'm requesting you for tomorrow.
Okay, how do I share screen?
Divjyoti sir, please do the needful for sharing screen.
Sir, there is a green button at the bottom. You can that one, and then you can choose the slide or the desktop, whatever it is visible.
Okay, can everybody see the slides?
Yes, sir, perfect.
Okay, thank you. So I'm going to talk about data envelopment analysis, a non-parametric approach to measuring efficiency. Data envelopment analysis was introduced in 1978 by Churns, Cooper, and Rhodes. Churns and Cooper were very established senior scholars in mathematical programming and operational research. And Eduardo Rhodes was their graduate student at Carnegie. And they were looking at how to measure efficiency in resource utilization in education, and their objective was to compare the efficiency of a group of schools which were participating in a federal program called Program Follow Through, which was targeted to children from minority families, with another group which was not a participant in the program. That was 1978, and that was in the second issue of now famous European Journal of Operational Research. At that time, I was a first-year graduate student at UC Santa Barbara, and my advisor, Professor Jyoti Sengupta, told me, Subhash, there is a new model, you might want to look into it. And that's how I got introduced into the methodology of data envelopment analysis, and that was 1979. Now, neither Professor Sengupta nor I, or not anybody around me, knew anything about data envelopment analysis. So I have been sort of a minor participant in the development of data envelopment analysis right from the beginning. And then I got a student project from the department head of the university. They were participating in an United Nations development program comparing healthcare, public healthcare provision in the countries of Guatemala and Costa Rica. And they were using regular econometric methods. And I explained to them that there is another way to measure the performance of the different groups of hospitals. And that was my first project in data envelopment analysis. Now, over the years, data envelopment analysis has evolved into an alternative to the standard econometric method of stochastic frontier analysis, and it has provided a way to measure efficiency in resource utilization without actually specifying any kind of a production cost or profit function. So there are two approaches to data envelopment analysis. One is the approach taken by operations research people who see data envelopment analysis as an algebraic mathematical problem. And the others like us who see data envelopment analysis as just another way to calibrate and validate or repudiate conclusions drawn from neoclassical production economic theory. In many conferences, my fellow participants have accused me of being too much of an economist, a stigma that I have been wearing with pride as a badge on my front. Because I am a neoclassical production economist first, I am a neoclassical production economist last. And all my interest in data envelopment analysis is really a way to quantify and to model further properties of the neoclassical production economic theory. So that's a long introduction. So let's start with this. Suppose that you want to know how a producer is performing. You have data. You are starting with data. A farm, let's say an agricultural farm, uses a certain bundle of resources, labor, capital, etc., to generate a certain quantity of output. A popular measure of output is the total value of the crop produced. Now, the question is, how can we say how the farm is performing? One approach is to compare its performance with those of other firms in the same industry operating under similar conditions. A frequently used criterion is output per worker, which is essentially labor productivity. Another measure of performance in agriculture in particular is output per acre. Now, here is the question. Let's say that I am working in an orchard collecting fruits. I am working 4 hours and have collected 10 bags. So you would say that Subhash, he has been collecting 2.5 bags per hour. Now, is that good? Is that bad? You don't know. It's just an information. It's a descriptive measure. But if you find that Shravanti, Professor Maiti, she has been working 3 hours and has collected 9 bags. Now you can say that Professor Maiti has been collecting 3 bags per hour. So although you don't know whether Professor Maiti's performance by itself is good or bad, you are able to tell that her performance is better than mine. So productivity is generally useful only in a comparative sense. That we all know. Now, a different approach to construct is to construct a benchmark. And there you ask, okay, Subhash has worked 4 hours and has collected 10 bags. And you are not comparing me with Professor Mathi or anybody else. You are asking, is 10 bags of fruit collected in a period of 4 hours of labor the maximum that could have been collected? So you are actually comparing me with my shadow, an abstract whom you don't see, but that is your standard. That is your benchmark of comparison. And when you compare the actual with what is considered to be maximum producible, what you get is efficiency. So you are not comparing output over input across 2 different individuals where the input quantities are different and the output quantities are different. You are comparing the output over input across a person who is actually observed against a standard where the input quantities are the same and the output for the standard is always greater than or equal to the actual output that you observe. Why? Because if you observe that I am collecting 10 bags, then it must be true that the maximum number of bags collectible over 4 hours cannot be any less than 10, because then how am I doing it? So the maximum achievable is always greater than or equal to the actually observed. So that is a measure of efficiency, and I am going to talk about it. So essentially, what we are really talking about are 2 different, 2 closely related, but different measures. One is productivity and the other is efficiency, and they are not the same thing. They are not the same thing. However, I am going to explain further. So productivity, by far the most commonly used and also the most easily understood measure of performance is productivity. In the simple case of a single output produced from a single input, it is merely the ratio of the output and input quantities. So now, going back to my example, a producer with a higher output per unit of input is more productive and is considered to perform in a superior fashion. Now let's take a simple example. Suppose that I see the input and output data for 5 firms A, B, C, D, and E. And their input output quantities are 15, 12, 10, 13, 10. And their corresponding input labors is 4, 5, 8, 7, and 9. So the average productivity, you simply take the ratio of output over input, and you find that the average productivities are 3.75, 2.40, 1.25, 1.86, 1.11. Now, firm A with the highest average productivity of labor performs best, and firm E does the worst. Here you can see that A has the highest average productivity, 3.75, and E has the lowest average productivity, 1.11. Now, in fact, average productivity becomes a measure useful for performance evaluation only in a comparative sense. For example, look at the firm D. If I just told you that D is using 7 units of labor, D is using 7 units of labor to produce 13 units of the output, and his productivity is 1.86, and all you can say is, oh, that's all. But only when you are told that A and B and C are producing this and their productivities are 3.75, 2.4, etc., then you can say that D is performing worse than A and B, but better than C. So average productivity is a useful measure of performance only in comparison to other observations. Now, let's take a slightly more complicated thing. Suppose that the output was not produced by labor only. In fact, very few instances will be there where the output is produced from a single input. So I come back and I tell you, oh, I forgot. Actually, they are each of these firms, A, B, C, D, and E, apart from using labor, were also using capital. And I'm sorry, I forgot to record them. So here is the full table. So here you see, I have got exactly the same quantities of output as I reported in table 1, the same quantities of labor as I reported in table 1, but now I have an additional row where I have got the corresponding quantities of capital. Here you have got two measures. One is output per worker, and the other is output per machine hour. So there is the average productivity of labor and the average productivity of capital. Now you can anticipate the question that I am going to raise. So who is a better performer? Now, clearly, if you stick to average productivity of labor, then A is a better performer than B. But if you look at the average productivity of capital, then B is a much better performer than A. In fact, D is even a better performer than A if you're thinking about the average productivity of capital. So this is this is often this is not a trivial question. We often talk about the enormous difference in productivity in agriculture between advanced Western countries like USA and the less developed agricultural economies like Bangladesh or India or places like that. But there, what we do is that we generally look at output per worker or output per acre and ignore the complementary inputs like fertilizers and irrigation and things like that. So if you take a farmer in Iowa in the United States, that farmer produces a much bigger quantity of wheat per acre than a farmer in rural Mexico. But in rural Mexico, the farmers use much less of fertilizers and machinery than the farmer in the Midwest in the United States. So how do you compare their productivities when you have got inconsistent ranking depending upon whether you are measuring output per unit of input 1 or output per unit of input 2? So when productivity is measured as output per unit of capital, then B is the best and A slips to the third position compared to when output is measured per unit of labor. Now, so what we need is an aggregate measure of input. So I do not want to measure output per unit of input 1 or output per unit of input 2. I want to measure the output per unit of the total input. So in other words, what we need is some way where your quantity of labor and capital is aggregated into a single measure, a quantity of total output. So the question is, how are we going to aggregate the inputs into a scalar measure? Now the task is very simple. When input prices are available and all firms face the same input price, then we can use the cost as a measure of the total input. So you would say that the total amount of dollar expenditure is the aggregate input, and so the average productivity is the quantity of output, let's say bags of wheat produced per dollar of expenditure on inputs. Here, let's look at this. Suppose that the price of 1 unit of labor is $150 per day, and the price of 1 unit of capital is $60 per hour. So here we have got exactly the same information that we had in the previous table, but now we are multiplying the labor quantities by 150 and the capital hours by 60 and adding them. So these are so 4 units of labor and 9 units of capital are aggregated into $1,140 of total input, and similarly for the others. Now we want to find out, so if you call labor and capital little x1 and little x2, then the big X, which is the aggregate of x1 and x2, where the aggregation is done by multiplying the input quantities by their corresponding price, then cost is the big X, and the output divided by cost is actually the inverse of the average cost. So the highest output per dollar corresponds to the lowest cost per unit of the output. Therefore, you can see that the lower the cost per unit, the lower the average cost, the higher is your productivity. And by this account, we see that B dominates A in the sense that B has a lower average cost, although A is a close competitor, whereas the other ones have got much more. So this is simple and easy to understand. Now, but there are several problems. When the different firms face different input prices, then the average cost difference need not necessarily be the reflection of actual productivity. Say, for example, why do the firms in the US outsource their garment industry to Bangladesh and the other countries in Southeast Asia? It's not because the workers in Bangladesh are more productive than the workers in the steel or garment industries in the United States. It's because the costs, the wages and the associated costs are much lower. So what you get as a lower average cost need not reflect what the productivity difference is. Then there are other cases where you do not really have any usable price for an input. Say in the United States, there is a lot of interest in the efficiency of the public school districts in the country. As many of you know, and many of you may not, in the typical structure of education, primary and secondary education is that if you are a resident of a town, if you are living in, say, my town of Mansfield, Connecticut, then you are automatically admitted to the local school. And only if you choose not to do that and send your child to a private school where the tuition often exceeds or compares with the tuition in Ivy League colleges like Harvard or Dartmouth. So most of the time, most of the students, they go to the school district and where they live. So there is a lot of interest, and you don't pay any tuition. You don't pay any tuition because the schools are funded by the municipal government, and also they get the offset from the state government. So there is, in each school district, there is a education committee, and they report the performance. So essentially, as the taxpayer in the city, I am interested in finding out how efficiently my school is run. And typically what you do is that you look at performance in the different different cognitive tests like English writing and math and comprehension. So these are imperfect, but the best measures of performance that we have. And for inputs, we use the number of teachers, the number of support staff, because the support staffs in the schools are very important. The counselors, the nurses, because we have got, for students with disability or for students who are not native English speakers, there are special coaching, and you need counselors for that. And then you have got the administrators. So we are able to identify the different inputs, and you can find out what is the rate of remuneration for these inputs, and you can think about the total cost. But you also know that a student's learning doesn't come only from school instruction. It also comes from the parental attention, how much time the parents spend monitoring and helping the student with homework and things like that. And there is no way you can measure, even if you are able to find through a survey as to what is the average number of hours the students were spending with their parents doing the homework. There is no way you can find out what should be the price of that input, the parental instruction input. Like they used to say for the credit card, MasterCard at one time, that 2 tickets to the ball game, $50. 2 hot dogs and soda, $20. An afternoon with your son, priceless. For everything, there is MasterCard. So much the same way, the time that you spend with your child, there is no price we can attach to it. But we may be able to find how many hours on average. So we need to find an aggregate of the input when we have some quantitative measures of the inputs, but do not necessarily have the prices. Now, the aggregation of the input quantities must satisfy 2 basic conditions. First, they must be homogeneous of degree 1. Now, what does that mean? That means that suppose you are looking at 2 inputs, x1 and x2, and their quantities are x1 0 and x2 0. Now, if x1 0 and x2 0 are both doubled, then no matter how you aggregate them, the aggregate also should be exactly doubled. That is the idea of homogeneity of degree 1. And second, the aggregate input must be monotonic. That is, it must be increasing or at least not decreasing in inputs. In other words, if you are using at least one input more than I am using, then your total input, no matter how you are aggregating, is typically more than my total input. Or in the extreme case, you might say that there is strong complementarity between the inputs, and therefore increasing an input without increasing the other does not increase. It's like, say, you have got people who need a shovel to work in the field. So if you have got 10 people and 10 shovels, that is 10 workers equipped to work in the field. If you have got 10 people and 11 shovels, it's still 10 workers equipped to work in the field. However, you cannot say that it is less than 10 people equipped to work in the field. That's what we mean, that this is weakly monotonic. So these are the two things that we need. Now let us look at this in the following way. You'd say that why not we do the same thing? Let's forget about the aggregate. We have got for each of the firms the average productivity of labor. And for those firms, we have got the average productivity of capital. Because these are actually ratios, let us take a geometric mean of the two. Instead of taking a simple arithmetic mean, let's take the geometric mean of the two. Now, not just an equally weighted geometric mean, but some unequally weighted geometric mean. So let's say that I assign the weight beta 1 to the average productivity of labor and beta 2 to the average productivity of capital. Then the total factor productivity, which is a geometric mean of the average productivity of labor and average productivity of capital, where the weights used are beta 1 and beta 2, it will be y raised to beta 1 plus beta 2 divided by k raised to beta L raised to beta 1 and k raised to beta 2. But beta 1 plus beta 2 is 1 because the weights must add up to 100%. So then what you get is that the total factor productivity, where y is the output, is y divided by big X, the aggregate input, which is L to the beta 1 and k to the beta 2. As you can see that obviously, so long as beta 1 and beta 2 are strictly positive, any increase in X1, in L, or any increase in K will increase the aggregate input X. Also, given that beta 1 plus beta 2 add to 1, if you multiply both labor and capital by 2, then the aggregate input gets multiplied by 2 to the power of beta 1 plus beta 2, which is just 2. This is a Cobb-Douglas aggregator. So one possibility is to use the Cobb-Douglas aggregation. That's not the only one. So now you are comparing me with the other person, let's say Professor Maiti, and you want to find out how does my productivity compare with her productivity. So this time what you are going to, let's say I'm person B and she is person A. So you are looking at the total factor productivity of B divided by the total factor productivity of A. So as you can see in this formula, this is YB divided by LB to the beta 1, KB to the beta 2, and YA divided by LA to the beta 1 times KA to the beta 2. So this actually is YB over YA and LB over LA raised to beta 1, KB over KA raised to beta 2, and the numerator is the ratio of the inputs and the denominator is the input quantity index. So here, the total factor productivity index is a pure number because our outputs are measured in bags of potato. So 10 bags of potato, 9 bags of potato, 10 over 9, it's a pure number. Our inputs are measured in labor days and machine hours. So my labor days divided by her labor days is just a pure number, and my machine hours divided by her machine hours is also a pure number. So this is a pure number, the denominator is a pure number. So you are going to get some number, and let's say that this number turns out to be 1.5. What does that mean? That means that her total factor productivity is 50% higher than my factor productivity. So the total factor productivity of any individual, that is my output divided my aggregate input, does not make much intuitive sense. But the total productivity index, the total productivity index essentially means that if my productivity, total factor productivity is considered to be 100, what would be your total factor productivity? That is 150. So that clearly means that compared to me, who is set as the standard, you are 50% more productive. Now, here, as you can see, the weights are of crucial importance. The weights are of crucial importance and can have a significant impact on how the total factor productivity is measured. When cost information is available, one can use the share of each input in the total cost as the weight. So not everybody will have the same cost share. If you look at it, you can find out that the total cost of A is 1140 and its share of labor is 600. The total cost of K, the total cost of B is 870 and its share of labor is 150 times 5, which is 750. So here you can see that B has a much bigger share of labor than A. But we can take the average across them. And if we do that, in this example, the share of labor on average across these firms is 72%, and the share of capital is 28%. And if we use beta 1 to be 72, which is the weight assigned to labor because it has got higher cost, and beta 2 equal to 0.28, then we get these total input is actually this 4 and 9, geometric mean, weighted geometric mean of 4 and 9 with weights 72% to labor and 28% to capital, and similarly for the others. And now if you take the output and divide it by this aggregated input, you get the total factor productivity. And here, if you have got the total factor productivity of B equal to 3.10, and total factor productivity of A equal to 2.99. Therefore, compared to A, B's productivity is 1.0368 or B is 3.68% more productive than A. Now, while useful as a relative measure of performance, productivity has got two major limitations. First, in general, the units of measurement of the aggregate input is undefined. Let's say that you have got three inputs. You have got labor, which is measured in man days or hours, and fuel, which is measured in gallons, and capital, which is measured, machines, which is measured in horsepower. So now you are taking a weighted geometric mean of hours of labor, capital, and fuel, beta 1, beta 2, and beta 3. and you are giving me an animal, and I don't know what animal is that, because I don't know this is so many units of what. So there is no intuitive interpretation of the aggregate input. So that is one of the limitations of productivity per se. Second, a comparison of productivity of two different firms does not tell anything about how much output a particular firm should be able to produce. Let me explain to you by comparing B with C. In B, for firm B, total factor productivity of firm B is 2.48 times the total factor productivity of firm C. Now here you are coming to firm C and you are saying that, look, B is the most productive one, and you should try to emulate the best performer. You should work like B. You should work like B. What does that mean? Are you really telling me that the output divided by an aggregation of the two inputs 8 and 8, I should be able to produce? So the total factor productivity of B compared to A is 2.48. Now C is producing only 10. So are you telling me that C should be able to produce from 8 units of labor and 8 units of capital, 24.8 units of the output? No, you really cannot say that. You really cannot say that, because their input bundles are quite different. And I will get to that very soon. A more appropriate measure of the performance is efficiency. So essentially what you do, as I said, is that you compare the actual output Y0 from some input X0 with what you consider to be the maximum producible output from the same X0, which is Y star. Now, obviously, Y star is greater than or equal to Y0, so that the ratio Y0 over Y star, which we call tau, the measure of technical efficiency, will lie between 0 and 1. Obviously, unless your output is 0, the tau will be a number bigger than 0. And because Y0 cannot be bigger than Y star, tau will be less than or equal to 1. Now, in order to operationalize this, obviously the question, you would say, Professor, this is easy, but where am I going to get this Y star? So let us say that Y star, there is some underlying function, the production function, where you tell me what is your X1 and X2, and I can tell you what is the Y star. At this moment, don't ask me, where did I get it? Suppose that my grandmother told me, and I will tell you where I get it. But at this point, let us talk in vacuum. Suppose that I have a formula that gives me what is the maximum producible output from a pair of inputs X1 and X2. Then using that as Y star, my output is actually Y0 divided by the value of the production function at X10, X20. So here, let's say that I know the production function, and in the single output, single input case, this curve is showing the maximum output that can be produced from their different quantities of the inputs. Now compare A and B. A is using XA, producing YA. B is using XB, producing YB. Now, when you are making a productivity comparison, you are looking at YA over XA, which is the slope of the OPA line, versus YB over XB, which is the slope of the OPV line. So you are comparing the slope of these two rays through the origin, and whichever is steeper and how steeper, you are able to find out what is their relative productivity. When you are measuring efficiency, you are keeping X fixed. And you are saying that from XA, A is producing YA. And according to this production function, the maximum anyone can produce from XA is YA star. So A's efficiency is to be computed by comparing YA with YA star, where the input is fixed, but the actual output is being compared with the maximum output. Similarly, B's output is to be compared with PB star, keeping XB constant, what is the actual and what is the maximum producible. These are, so YA divided by YA star, which is less than or equal to 1, is the efficiency of A. YB over YB star is the efficiency of B. And these are the technical efficiencies. Now, you might say, I am not interested in increasing output because I do not have the market. I want to reduce inputs. Say, for example, going back to my example of the high schools in the United States, the schools do not recruit students. They have a certain population. That population has a certain number of children of school-going age, where going to school is compulsory. Therefore, the number of students is given to me. I want to find out what is the minimum number of teaching hours that I need to successfully teach these students. So here you are producing YA and you are using XA, and you want to know what is the minimum quantity of X that you need to produce YA. So this time, instead of going up, you are going to the left. And here also, instead of going up, you are going to the left. So you know that the minimum required cannot be any more than the actual, because the actual is already producing YA. So to produce YA, you either need the actual or less. So this time you are measuring OXA star over OXA. You are comparing PA star with PA, and similarly PB star with PB. These are the input-oriented efficiencies. How much? So output-oriented efficiency is like the maximum producible is 100, and I am producing 67. Therefore, my output-oriented efficiency is the actual divided by the maximum, which is 67%. Input-oriented efficiency is how much is needed divided by how much is used. I am using 50 units of the input. All I need are 45. Therefore, the input-oriented efficiency is 45%. So the input-oriented efficiency means what proportion of your actual input is really needed. The lower this ratio, the greater is the waste. That is, you are using more input than you need to. And that is a measure of inefficiency. On the other hand, when you are talking about output-oriented, there you are achieving only 80% of the total achievable output. So output efficiency shows the shortfall from the total potential. Input efficiency shows the excess. 1 minus the input efficiency shows the excess. So input efficiency shows what proportion of the input is really required. Here is a numerical example. Suppose that the production function is y star f of x is equal to 10 times square root of x. And a firm is using 9 units of x to produce 24 units of the output. So here you can see that from 9 units of x, you should be able to produce 30 units of the output, 10 times square root of 9. So your output efficiency is the actual 24 divided by the maximum 30, which is 80%. Now, you want to know, I do not want to change my output. I am using 9 units of the input. Could I produce the 24 units of the output with less than 9 units of the input? If so, how much? So what we do is that now we have got y as a function of x. We invert this as x as a function of y. So we get that x, the minimum quantity of x, is y squared divided by 100. And you have y equal to 24. Therefore, the minimum quantity required is 24 squared divided by 100, which is 5.76. So this tells me that I am using 9 units of the input to produce 24 units of the output. But according to this formula, I should be using only 5.76 units of the input to produce the 24 units of the output. Therefore, my input-oriented efficiency, my minimum required divided by my actual is 5.76 divided by 8, divided by 9, which is 64%. Notice that the output-oriented efficiency and the input-oriented efficiency, they can be different. They are not in the case of constant returns to scale, but I will talk about that in a subsequent lecture. But the question, of course, is where am I going to get the benchmark? So this is almost like A is asking, how is your wife? And B is responding, compared to what? So how is the firm doing? Depending upon what are you comparing the firm's performance with. Incidentally, these are both two senators from Illinois who became president. This is Abe Lincoln and this is Barack Obama, standing for A and B. Now here is the relation between productivity and efficiency. It's important to note that production function, if the production function does not exhibit constant interest to scale, higher productivity would not necessarily imply higher efficiency. Take this example. Suppose that one unit of one input x1 is needed to produce the output y. Firm 1 uses 4 units of the input to produce 15 units of the output, and firm 2 uses 24 units of the output from 9 units of the input. Therefore, the average productivity of 1 is 3.75. The average productivity of 2 is 2.67. So A is more productive than 1 is more productive than 2. But surprise, you will find that 2 is more efficient than 1. Now suppose that the production function is f of x equal to 10 times square root of x. I'm talking about a single input. In this case, the maximum producible output from the input used by firm 1 is 20, and its technical efficiency is 15 over 20, that is 75%. On the other hand, the maximum output producible from 9 units of the input is 30, and the technical efficiency of firm 2 is 24 over 30, which is 80%. So here you see that 2 has a lower productivity, but has got higher efficiency. Now, this anomaly arises because of the fact that the production function exhibits diminishing returns to scale. Average productivity would decline even if you are on the frontier and there is no technical inefficiency. So unless constant returns to scale holds, technical efficiency is a better measure than productivity for performance, because you are blaming me simply because of my size. Because when the scale is higher, the average productivity is lower. As you can see in this diagram, the average productivity, the slope of the line connecting the point with the origin is steadily declining because of diminishing returns to scale. So even if I was here and you were here, I would still be having a lower average productivity, although we are both efficient, simply because diminishing returns to scale. Now, stochastic frontier analysis, there are two approaches. One is the econometric approach, where you specify a production function and then you estimate the production function, and then compare the actual with what is predicted by the value of the output according to the production function, and the other is the non-parametric approach. Now, typically what we do is that if you take the Cobb-Douglas production function, then you write this as log of y is alpha plus beta 1 log of x1 plus beta 2 log of x2 plus v minus u. I'm going to tell you more about this. So essentially what you are doing is this. You are saying that y star equal to some function of x given the parameters beta 1, beta 2, etc. But that is not cast in stone. The maximum output producible from the same x for the same technology will be higher because of random shocks which are favorable. Like in a good monsoon year, the same labor, capital, land, fertilizer will give you more output. In a drought year, the same labor, capital, and land and fertilizer would give you less output. So f of x beta is on an average year, and a positive v is going to push the frontier up, a negative v would push the frontier down. That's why it is called the stochastic frontier. But the actual will always be on or below the frontier that is applicable for your particular situation. And that is captured by this minus u, where u is a non-negative term. So this is the so-called composed error. This is a two-sided disturbance, and this is a one-sided disturbance. V can be positive or negative, going from minus infinity to plus infinity, and you can only be positive, so that you will always be odd zero. So you will be always on the frontier or below the frontier, but not above the frontier. Suppose that this is your f, and this is the frontier for the average year. Now, if you have a favorable shock, the frontier moves upwards. If you have an unfavorable shock, the frontier moves downwards. Now, depending upon whether we are talking about a good monsoon or a bad monsoon year, we are having. So here is the frontier for a good monsoon year. V is positive, and the red dotted line is let's say that your efficiency is 15%, 85%, which essentially means that from every input bundle you are producing only 85%, that is 15% lower than what would be possible if you were not inefficient. So this is this would be the observed output when you are having inefficiency. And similarly, you have got this as the bad year frontier, and you are below the bad year frontier in a bad year by the level of your inefficiency. This is the idea of the stochastic frontier. Now I won't get into this thing. Typically what econometricians like my friend Subal Kumbhakar, what they do is that they take a function and they assume that the u has got the normal distribution, and v has got the normal distribution, the standard, and u is some one-sided distribution, so which is like the normal distribution truncated at 0 from below. So that is the log likelihood function, and that's a completely different industry, and we won't get into that. Now we go to the approach where you measure efficiency without assuming any production function. Validity of any estimated stochastic production frontier as a benchmark is meaningful, it depends upon whether the function that you specified is correct. Now, choice of the preferred function specification is often arbitrary and is driven by computational simplicity and tractability. Well, this reminds me of a story that many of you have read. This is the story of the famous, I believe, fictitious character Mullah Nasiruddin. Mullah Nasiruddin was once found by his neighbor frantically looking for something in his garden in the evening. The neighbor, being a friendly neighbor, came to Mullah and asked him, "What are you doing?" He said, "I dropped my keys and I'm looking for it here." Again, being a friendly neighbor, he tried to help Mullah, and for half an hour, he was also searching for his keys and didn't find. And then he asked Mullah, "In which part of the garden do you think that you dropped the key?" And the Mullah said that, "I dropped it in my bedroom." And so the neighbor asked, "Then why are you looking for it in the garden?" He said, "You are really stupid, because the bedroom is dark. In the garden, there is so much more light. It's so much easier to look for it in the garden." And many times my stochastic frontier friends, they pick up the Cobb Douglas not because they believe that it is the correct production frontier, but it is much easier to estimate it. So what we will do is that we will not estimate any production frontier at all. We will just look at the data and make a number of assumptions and use the data, and on the assumptions, and based on the assumptions, we will try to say that this firm is found to produce this much output from this much input according to the assumptions that I have made, and based upon the data, this firm should be able to produce this much output from this input. And therefore, the number that I come up with and where I compare with is the efficiency. So here, let's look at this. Firms A, B, C, D, and E, these are the output and input. Our objective is to construct the production frontier for measuring the technical efficiency of the firms in the data set based entirely upon just these 5 observations, making no specific assumption about what is Y as a function of X. But of course, you have to make some assumptions. So we make 4 assumptions. All actually observed input-output pairs are feasible. That is, it is possible to produce 10 units of output from 4 units of labor. It is possible to produce 8 units of output from 7 units of labor, to produce 16 units of output from 12 units of labor, and so on, because this is actually seen. You are seeing that somebody is doing it. So what is observed is feasible. Second, increasing the input quantity will not lower the output. That is our assumption, that you can, if you are producing output Y0 from X0, and if I give you some more input, you can just keep it idle and still produce the whole quantity. Third, if you are producing Y0 from X0, and if I ask you to produce a little less, you can gladly do it. Again, it reminds me of an experience that I had in the international airport in Dhaka, Bangladesh. I, another Indian, and a British woman, we were waiting for our connecting flight to the US, and we were given, because it was a long connection, it was they gave us something to eat, and it was a chicken leg and some fried beans, no bread or anything. And putting me and the other Indian to shame, the British lady said, "I'm a vegetarian, I don't eat chicken." The waiter said, "No problem, madam." He just picked up the chicken leg and went away. So you can always reduce the output from the same resources. This is known as free disposability of output. And finally, this is a little bit of a contentious assumption, but it's not entirely, which is that the production possibility set is convex, by which we mean that if I take your input output and my input output, and if I take a weighted arithmetic mean of your input and mine, then the corresponding weighted arithmetic mean of your output and mine can be produced from this weighted average input. This essentially, I am not saying that this is the maximum that can be produced. I am saying that it can be produced. This is known as the convexity property. So these are the 4 assumptions that we are making. And you will see that there are hundreds and hundreds of production functions, all of which satisfy these assumptions. So these are a very weak set of assumptions. Now let us look at the following slide to decide how these assumptions allow me to measure efficiency. First, these are the actual input-output quantities of A, B, C, D, and E. And by my assumption 1, measuring input along the horizontal axis and output of the vertical axis, I can clearly see that I don't know what other input-output combinations are possible, but these 5 are always possible because they are actually seen. Next, I jump to my assumption 4, which is that the weighted average of any pair of observations and weighted averages of those weighted averages are always feasible. That means that the entire area bound by these points A, B, C, D, and E is feasible. Notice that a point like this, I didn't see. I didn't see a combination of, say, 8 units of the input with 12 units of the output. But by implication, because it is in the feasible area, it is feasible. So just these 2 assumptions, that the actual is feasible and their weighted averages or convexity, this is known as the convex hull of these observed input-output bundles. Then what I am going to do is I am going to say that, okay, we first started with these 5 points which are feasible, and then we said that the closed area, all points on the closed area along the boundaries and inside are feasible. And then we said that, then we said that because it is possible to produce the same output with more input, I can take any point in this area and move to the right. Notice that I'm not moving up, I'm just moving to the right, which essentially means the same output is being combined with greater input. So all points to the right of this closed area would be feasible. And finally, we are saying that if we take any feasible input-output and lower the output without changing the input, that is moved downwards, all points will be feasible. And then what you get is this. So this is a boundary or the frontier which is constructed from these data, these 5 data points, and the 4 assumptions that we have made. We didn't assume anything, and all of these assumptions are valid whenever you take one of the standard production functions. So now you can say that A is on the frontier, C is on the frontier, B is below the frontier, and you should be able to move from 8 to 12. E is below the frontier, maybe 7, and you should be able to move to here. D is below the frontier, you should be able to move to here. Now you might ask me, but how do you know that this is the maximum? How do you know that you cannot go above this? I don't. But in order to argue that you can move above this, you will have to make additional assumptions which may or may not be valid. It is almost like It is almost like, suppose that I told you that a man jumped from the top of the hill beside the Niagara Falls into the river on a very rainy night. What will definitely happen to him? You might say that he will die. Not necessarily. He might still survive. But one thing that can never happen is that he will remain dry. He will be soaking wet, no matter what. Exactly the same way what I am saying is that the maximum producible may be way above this, but it can never be below this. So what I am doing is that I am giving you the most favorable benchmark. I am giving you the most favorable benchmark, the lowest upper bound. And so this provides the lowest upper bound based upon my assumptions. And so what is the difference between regression and DEA? Why is this called data envelopment analysis? Now you see that we have the data points and we have created an envelope or a frontier which covers all the data from above, but as close as possible. Because if you move any below, any further, you will not be able to cover all the data points by the line. And this is the difference between regression and DA. In regression, you draw a line through the points so that some lie above and some lie below. You minimize the sum of the squared deviations, allowing deviations to be positive and negative. Here, you draw the line such that no point lies above the line, and actually there is a piecewise connected line. And at the same time, you make the points as close to the data as possible. So I will go to the next slide and then I will give you a break and you can ask me questions or whatever. So the frontier constructed using data and the assumption 1 through 4 is called a non-parametric frontier because you do not specify any explicit function for Cobb-Douglas or some other production function. Now return to the question of measuring technical efficiency of farm E. The benchmark for comparison would be the 0.5 star. This is the point P5, and you are going to this point above, and that would be the point of comparison. And the input quantity is 7, but the output produced is 20. It can be seen that the input-output bundle P star, P5 star, X equal to 7, Y equal to 20 is a weighted average of the input-output quantities of farm 1, where X is 4 and Y is 8, and farm 3, where X is 8 and Y is 24. And the weights attached are 0.25 and 0.75. So let's look at farm 1 and farm 3 and look at this 25%, 75% weighted average. Farm 1, you give 25%. So essentially 1 input and 2 units of the output. Farm 3, 75%. So 6 input and you get 18. So you are ending up with 2 plus 18, 20 units of the output, and 1 plus 6, 7 units of the input, which is 7 units of the input of farm 5, but the farm 5's actual output is 11. So you are saying that by creating a 1/4, 3/4 weighted average of farms 1 and 3, I can create an input-output bundle, which I don't see, but by my assumption is feasible, which will use 7 units of the input exactly like farm 5, but will be producing 20 units of the output. So compare 11 with 20 and you would say that farm 5's efficiency is 55%. Okay, so let me at this point give you a break and
okay, participants, if you have any question, please ask.
Hello, sir. Hello.
Yes, yes,
Ma'am, am I audible?
yes, you are.
Sir, actually, we are new to this data envelopment analysis. Sir, like, it seems that it is a economics term, something related to economics, where like we are going with the help of that. I think we are going to measure the efficiency, technical efficiency, cost efficiency, like that. Sir, can we use this DEA for marketing in HR, sir? In what way it can be applied to marketing and human resource management?
my question is, how do you apply economic theory to marketing? Anytime you can apply neoclassical production economic theory, you can apply DEA. DEA is not a theory, DEA is a tool. The theory is the neoclassical production economic theory. So cost efficiency comes from the theory of cost. And what is the theory of cost? Minimize W1 X1 plus W2 X2 subject to f of X1 X2 is greater than or equal to target output Y. So what we are doing here, as you will see, I think you have a very valid question, but you are not patient. In order to answer this, you cannot get this in 30 minutes. You have to read my entire book, which I published in 2004, which is the data envelopment analysis theory and techniques for economics and operations research, where I have got specific chapters for all of them. But the answer to your question is, you are going to articulate your question as a production economic theory question. And until then, there is no choice between DA and SFA. Once you get to an estimable relationship, the choice is between, do I go econometrics? Do I go mathematical programming? Does it answer your question?
Yes, sir. So that means we can use it in finance, sir. Like that. We cannot apply in marketing or HR, but in case of finance, there we can apply this.
Certainly you can apply in marketing. Certainly you can apply in marketing. There are tons of papers in marketing, especially the marketing science journal and all that. Say, for example, you can try to find out, you are trying to maximize sales. And you have got sales employees, you have got advertisement expenditure, and you have got what you can call an anti-input, which is the sales expenditure of your competitors. And you apply, you set up the model appropriately, and then you try to find out, given the amount of money that I'm spending on newspaper advertisement and TV advertisements and on, say, blogs, and given the counter advertisement by my competing brand, is it possible to increase my sales? And if so, by how much? Or in order to achieve this marketing goal, am I making the minimum expenditure? Or is it possible to cut down? And what mix of in the different media that I can use to achieve the same goal at a lower cost? There are tons of examples that you can do. But there is not going to be something like a Big Mac you go and pick up and apply. You will have to conceptualize this. You have to do your own recipe. Any other question?
Dr. Rachana, hello, Dr. Rachana, are you there? You have asked one question in the chat box.
Yes, ma'am, regarding the degree one, actually that time while sir was explaining now, I just actually got some technical issue. So I did not get what was that degree one. What
Say that
means,
again.
sir? Yes, sir.
No, say that again, please.
I was
You did-
asking in the slide, you explained the term degree 1. At degree 1,
homogeneity of degree 1.
yes, sir. So that concept of degree 1, actually, I did not get.
Oh, that is Euler's. So that essentially means that if you multiply, you have got x1 and x2, right?
Yes,
You have
sir.
got
Yes,
x1
sir.
and x2.
Yes,
Now,
sir.
if you multiply x1, let's say that you have the function y equal to square root of x1, x2. Now, if you multiply x1 by 2, x2 by 2, then the term inside the square root gets multiplied by 4. So if you take it out, y gets multiplied by 2. That is, if you multiply x1 and x2 by some factor t, then the function gets multiplied by t to the power of 1. Or it could be t to the power of 2. Say, for example, your y is x1 square plus x1, x2. Now, if you multiply x1 by 2, the first term gets multiplied by 4. If you multiply x1 and x2 by 2, the second term also gets multiplied by 4. So the y gets multiplied by 4, which is 2 to the power of 2. That is homogeneity of degree 2. That is the whole idea of homogeneity, homogeneous functions.
Okay, sir. Thank you, sir.
So should I continue, or there are more questions? Or
I don't
people want to take a break?
know, sir. You please continue. Is there any more question from anyone's else?
No,
Please
ma'am.
ask.
You can continue, ma'am.
Yes, sir. Please continue.
Okay. So now we are talking about, I'm sure if I were you, I would say that this is silly. Because after you made me sit for, I don't know how long, an hour, 15 minutes, and you ultimately drew some points and connected the points and say, go home. I could have done that without your all this big talk and all that sort of stuff. But now let us talk about one output and two inputs, where you really cannot easily draw a diagram and create the frontier. So a simple graphical analysis will not be possible, but we can set up as an algebraic problem to solve by an optimization method known as linear programming. So now I am taking the data from table 1, where you have got the same outputs, 15, 12, 10, 13, and 10, and you have got the inputs of labor and capital. So suppose that here is my data, and I want to find the efficiency of firm C. Firm C is producing 10 units of output from 8 units of labor and 8 units of capital. And all I know are the input-output quantities of these 5 firms. I don't know anything else. So it is almost like you have got observations of different units producing in the same industry, and you want to pick any one of them and ask, how is it doing? Let's say that you are the owner of the Subway sandwich franchise company. So you have got a number of Subway restaurants all across the city of Bombay. And you as the regional manager, you want to find out, let's say that your outputs are the number of sandwiches sold during lunchtime, and your inputs are labor and say some other input. And you want to say, how is the subway shop at the corners of a particular downtown area is doing. You are comparing them with the performance of all other subway outlets in the locality. And so these are the different ones. And you want to find out how is C doing. Now you can see that if I take a 2/3, 1/3 combination of A and D, because we know that by looking at A, 4 units of labor and 9 units of capital can produce 15 units of the output. And 7 units of labor and 6 units of capital can produce 13 units of the output. So what I do is that I create a hypothetical firm which is made up of 2/3 of A and 1/3 of D. So I take 2/3 of labor of A and 1/3 of labor of D, 2/3 of capital of A and 1/3 of capital of D, and the 2/3, 1/3 weighted average of the outputs. What do I get from this? What do I get is that the benchmark input bundle will be 5 units of labor and 8 units of capital. And the benchmark output would be 14 and 1/3 units of output. So now what I am doing is that I am taking the firm C, which is using 8 units of labor and 8 units of capital to produce 10 units of the output. And we are creating an imaginary firm, which under my assumptions is possible, which is simply a 2/3, 1/3 weighted average of the firms A and D that would use 5 units of labor, 8 units of capital, and would produce 14 and 1/3 units of output. Now, here you see that if it is possible to produce 14 and 1/3 units of output from 8 units of, 5 units of labor and 8 units of capital, if I compare it with C is also using 8 units of capital, but using more than 5 units of labor. C is using 8 units of labor. So if 5 units of labor and 8 units of capital can produce 14 and 1/3, then obviously 8 units of labor and 8 units of capital should also be able to produce 14 and 1/3. So if I compare the output of C, which is 10, and with the 14 and 1/3 or 43/3, then we find that C's efficiency is no more than 69.7%. So notice that I am not just saying C that you have to do better. You see, in general, what happens is that in performance evaluation, often individuals or production teams are told you have to do better. Now, what do you mean by you have to do better? Oh, well, you should be producing more output from your input. You should be using less input from your to produce the output. How much more? So don't talk in vacuum. Give me numbers. And how do I know that these numbers are possible? Well, I am giving you numbers. I am telling you that you should be able to produce 14 and 1/3 units of output using only 5 units of labor and 8 units of capital. Notice that this benchmark does not require you to use any more capital, but actually you will have surplus labor, but I am allowing you to, I'm not penalizing you for the surplus labor, but my objective is to see that you are able to produce this much of the output. And how can this be done? This can be done by creating a weighted average of A and D. Now, the thing is, often if you do this, people will say, tell me how I can do it. I'm not going to tell you how you can do it because you are on the job. I am just a consultant. You tell me why you cannot do it. If A and D are able to do these things, you give me a reason why you cannot do it. It's not my job to tell you how you are going to be like A. It's your job to tell me why. Is there any special advantage that A has or D has that you don't have? You identify that for me. I shift the burden from me to you. You tell me, because you both agreed. When we started this negotiation, we both agreed that what other people are doing, you should be able to do. And if you are given more input, you should be able to produce the old output. If you are asked to produce less output from the same input, you will be able to do that. And if we take a weighted average of what other people are doing, then the weighted average of the output should also be produced. We agreed on that on our first meeting. Now you tell me what is special about A or D that you do not have. It is possible. It is possible that A or D, they are located in some place which is right near the railway station, and you are located in a back alley. When phone booths were popular, people with phone booths back into a narrow alley had poorer advantage because that was locational advantage and that could not be transferred. But you have to tell me exactly what that advantage is, and then I will know whether or not you can do it or not. Just don't say that, oh, they are different. I am coming up with numbers. You come up with very specific reasons why you cannot act like them. Now, notice that here I have given you an example I have given you an example by just eyeballing. Okay. So I said that, look, here is one combination. 2/3 weight given to A, 1/3 weight given to D, and that creates an output input bundle where no input is required more and output produced is more. So that should be possible to do because you are getting no less than the target input output bundle. But the question is this the best combination? How do I know that there is not some other combination, weighted average of inputs and outputs, which would also require no more input than C, but would produce even more output than this 14 and 1/3? So in order to answer that question, we have to set up the following linear programming problem. So what I'm doing here is this. I am trying to maximize the scaling factor phi, which is the output expansion factor, such that these constraints are satisfied. Let me go over this slowly and one by one. Here you see that this lambda 1, lambda A, B, C, D, E, these are weights. And these weights, none of these weights can be negative. And these weights have to be 100%. But notice that some of these weights will be 0, but none of them will be negative. If a weight is 0, that essentially means that in creating the benchmark input-output bundle, I do not consider that farm. And the higher the value of a lambda, the greater is the weight that I assign to that particular unit. So this is this 1549, 1252, 1088, 1376 and 1098, these are the actual output, the actual labor, actual capital of A, and similarly for B, C, D, etc. And we know that because these are observed output input bundles, 15 output, 4 labor, 9 capital is a feasible input output combination. Similarly for the others. So these are feasible because they are observed. Those are like those 5 points that I did draw in the screen. Then I invoke convexity, which essentially means that if I select a number of weights such that no weight is negative, and the weights add up to 100%, then that weighted average of labor and that weighted average of capital can produce that weighted average of output, which essentially means that this weighted average of labor 4, 5, 8, 7, 9 with weights lambda A through lambda E, the similar weighted average of capital can produce the similar weighted average of output. Now, if this weighted average of labor and capital can produce this weighted average of output, and if I am giving you no less labor and no less capital, then this 8 can also produce this weighted average of the output. Now, if 8 can produce this weighted average of the output, and the right-hand side, 10 times phi, is less than equal to this weighted average, 8 can produce this 10 times phi. So what is the largest value of phi such that 8 can produce 10 times phi? Now you are going to say, wait a minute, I'm totally lost. So what are you talking about? What I'm saying is this. So let us now translate this into something that you can put into a simple newspaper. C is using 8 units of labor, 8 units of capital to produce 10 units of the output. And I want to find out, does there exist any weighted average of the observed input-output bundles which would require no more than C's labor and capital and produce phi times C's actual output? Now, you can see that because I'm trying to maximize, phi equal to 1 is always possible. Why? Because you can select lambda A, lambda B, lambda D, lambda E equal to 0, and lambda C equal to 1. Then this will be 10, this will be 8, this will be 8, and this will be 8, this will be 8, and you can set phi equal to 1, in which case you are going to say that don't do anything, just let it be there. But if phi is greater than 1, that essentially means that you can produce, let's say that phi is 1.2. Then that means that you can produce 1.2 times C's output, which would be 12, using no more than C's input, 8 units of labor and 8 units of capital. So the maximum producible output will be 10 times phi star, which is the optimal solution of this problem. And that will be producible from the actual inputs of labor and capital of phi of C. Now, in the previous LP, lambdas are the weights assigned. The left-hand sides of the 3 inequalities are the output input quantities of the benchmark bundle that is created by taking a weighted average. Our objective is to seek the weights that lead to the highest value of the left-hand side of the first inequality. Let me call it YC, without violating the other 2 inequalities. Hence, the technical efficiency of C, because the highest value is phi times YC, and this is YC, so that will be 1 over phi. So if the value of phi is 1 over 0.2, then that I'm sorry, 1.2, then that means that the maximum output producible from C's input is 20% more than what you are producing now. You're producing 10, you should be able to produce 12. And remember my definition of the output efficiency, that is 10 over 12, which is whatever it is, 0.865, 825 or whatever. So in this particular case, the optimal value which we are getting is not a 2/3, 1/3 combination of A and D. The optimal value is 85.7% of A and 14.3% of B, and no weight given to C, D, and E. And the maximum output, the maximum factor is 1.457. Thus, the technical efficiency is 1 over 1.457, which is 0.686. Now, 0.857, 0.143 weighted average of the bundles of arm A and B will produce 14.571 units, which will, while using the same as many capital and no more labor than C. Now, actually, it would require only 4.143 units of labor, which is 3.857 fewer. But we are not considering economy of labor is not, so long as you don't ask for more, I don't care. I am oriented more towards expanding the output. So here you can see that when you apply the linear programming process, then you are going to find that the optimal value is higher than what we originally thought, because originally you could see that my optimal was 0.697, but here you find that it is slightly higher. I mean, the optimal was 1. The actual over the optimal was 0.697. Here, the actual over optimal is somewhat lower, 0.8686, which means that the optimal is higher because the actual is the same as before. So you are able to get a higher output, which is 14. What was this? The 14.571, and the other one, earlier one, was 14.333. So if we choose these two weights, the maximum output would be slightly higher than what we would choose if we arbitrarily picked up the 2/3, 1/3. Okay. Now, we can also do a multiple output and multiple input, but this becomes much too theoretical. So let me just show you how we are doing the LP, and then I will continue this in the next class, okay? On tomorrow. So let me. While I'm looking for the data, am I still on or am I off?
Yes, sir. You are on.
Am I on, or is
Yes, sir.
still...
Yes, sir.
You can still see the screen?
No, sir.
See
No,
you.
sir.
Yes. Yes. Sir, your
Okay.
screen is not visible.
Okay.
It is not
let
shared,
me-
I think.
So how do we get back to screen share? How do I get back to screen share?
Sir, you have to share it once again by putting, by clicking on the green button.
How do I expand the little thing here? Because I can see the video, but how do I expand it? I have minimized it. Okay, share.
Share screen.
No, I have not been able to find it yet.
Sir, first you share the screen, then we'll be able to help you, sir.
No, but I am not able to get the Zoom screen itself. Somehow.
Sir, can you move your cursor?
Okay, I should be able to do this now. Yeah. I'm able to move the cursor. I can see you, okay. But unfortunately, it's a very small screen that I see, and I don't know how to expand it.
Sir, can you?
I obviously am connected with you, but
yeah,
I'm not able
to the share screen button at the below.
You see, in the at the bottom, I have got only my icons, which are, I don't see the Zoom icon, and so in the Zoom icon, it brings me to this, but I don't see the share screen.
Sir, just let me know, have you used the Zoom app or what else? You directly connect with the Zoom app or browser?
Do I have to connect again?
Let me know, sir, please. Have you connect with Zoom app or through browser?
Through browser, I think.
Okay, if you browser, no? So if you didn't find the share button in your screen.
Okay, let me. Okay, return to meeting.
Yeah, sure, sir.
Yeah, thank you. Okay, can you see this now?
Yeah, sir. Perfectly visible, sir.
Okay, here you see, I have got the data for the 5 firms A, B, C, D, and E. And I have got the output, the input of labor, the input of capital, and I have got the mathematical programming problem written up here, okay? I have got the mathematical programming problem written up here. First, what I'm going to do is that I'm going to create a column here, and let me just call it lambda. And these are going to be my choice variables, because I'm going to select the lambdas. Okay. The next thing I'm going to do are, I have got 3 left-hand sides and corresponding right-hand sides, right? So let me write here as I'm sorry. So these are my left hand and the right hand sides. Now, what are my left hand sides? The left hand sides are the sum product of the output column and the lambda column. And then sum product of the labor column and the lambda column, the capital column and the lambda column, right? So let me copy these names so that I know. So these are this is the output constraint these are the labor constraint and capital constraint. There is a total sum constraint, but we will get there. So what I do is that I write this as equal to the sum product. This is the sum product of the lambda column and the output column. Similarly, this is the sum product of the lambda column and the labor column. And finally, this is the sum product of the lambda column and the capital column. Now, of course, you could do each one of them one by one, like pulling tooth. But if you have got too many columns, that's boring, right? So what is happening is that we are fixing the lambda column, but doing a sum product of the column C, column D, column E, right? So why not, let's do this, equal to the sum product, drag over the lambda column, and before you move on, hit F4. Once you hit F4, you're fixing the, because now you see it is not F2 through F6, it is $F $2 through $F $6, comma, the output column. And we now simply copy these across. What this has done is that this has given me a sum product of the F column and the C, and the sum product of the F column with D, the sum product of the F column with E. I don't have to write it 3 times. Only the, as I am dragging along, the second array is changing from column C, D to E, but the first array doesn't change, it remains fixed. So those are, now I have got this. Why are they 0? Because right now my lambdas are all 0. This is blank. That's why the left-hand sides are all 0. What is the right-hand side? The right-hand side is actually the output and the inputs of the firm which is being targeted, the firm C, and the output is multiplied by the factor to phi. So first what I will do is that I will simply copy this, this one. But you are going to say that, sir, this is not the right-hand side. The right-hand side is phi times that. So I need to create a cell phi. That's another variable, but I'm sorry. But this is also my objective function. So I am giving this a special role. So my choice variables are the lambdas and the phi. And this is actually equal to this times phi. And I have got yet another constraint, which is that the sum of the lambdas have to be equal to 1. So if I want to write here sum, that is equal to the sum of the lambda column. So what I have done is that I've entered the left-hand sides of the constraints, the right-hand sides of the constraints. Although I haven't yet told anything, what are the constraints are like, that I will do in solver. Now, in order to do solver, what you should do is that you should have, when you click on data on ribbon, then there should be, in the ribbon, there should be something called solver. I presume that you don't have it. I presume that you don't have it. So first.
Yes, sir, we don't have it, sir.
You don't?
Yes, sir, we don't have it, sir.
Okay, exactly. That's what I'm going to say. Sure. So in order to bring solver, you go to file, go to options, go to add-in, and here you go to solver add-in, rather Excel add-ins. You click on go, and that gives you a list. And you will, if this in your case it probably is not checked, put a check mark on there and put OK. And now if you click on data, you should be able to find solver here. Are you able to get that? So file, options, add-in.
We did all the steps, sir, which you said, but I didn't get that option, sir.
Okay, let me show you again. File, options, add-in, Excel add-in, go, check on solver add-in. Okay. Now, are some of you using Mac? Because what I am giving you is for Windows. For Mac, there is a different way, and I will send the file to Shravanti today, and you might be able to do that. So those of you who are not able to get your solver yet, just follow this and look at what I am doing, and then you will be able to activate your solver add-in. I do not use a Mac, so I won't be able to show that to you. Okay. So now you have, I am presuming that at least some of you have been able to get solver. Is that correct? I'm waiting for an answer.
Sir, got it, sir. At the right end, after below data, below data analysis, that is, it's coming, sir, solver.
Okay, when you eat, so yes, you don't do data analysis. You just click on solver.
Okay, sir.
Once you click solver, you get this window.
Yes, sir, I got it. Yes, sir, got it, sir, got it, sir.
Okay, now what does this window ask? You can actually move it around, okay? So the window wants to know what is, in which cell is your objective function. So here you see, here you see that my objective function is phi, right? So my object, you bring your cursor here and click on the green cell. That's why I colored it green, so that you will know that that cell contains, because if you have a large program, you have to look around and find out which cell contains my objective function. Okay. So my objective function is in cell G, column G, row 5. Then it wants to know, is it a maximization or a minimization problem? Because we are maximizing phi, it's a maximization problem. So I leave it like this. Otherwise, if you are doing cost, or if you were doing the input oriented where we minimize theta, then we would do the minimization problem. Then we would actually click here. But right now we are not doing that. So now it wants to know what are the changing variable cells? Which are your choice variables? Now, in this problem, what are the variables that you choose? You choose the 5 lambdas and you choose phi. So my changing variable cells, you bring your cursor here and click on this. So that's one of my choice variables, comma, and then you drag over this. So that tells that my choice variables are in G5 and F2 through F6. Now you are going to add the constraints. And when I add the constraints, I have to click add. When I do that, it wants me to enter the constraints one at a time, but I have the advantage that for the output constraint, the left hand is greater than the right hand, but for both of the input constraints, the left hand is less than equal to the right hand. So first I write the left hand side of the output is less than equal to, so I don't have to do anything, the right hand side of the output. And then I add the other constraints. Notice that I could add the left-hand side of labor is less than equal to the right-hand side, the left-hand side of capital less than equal to the right-hand side, one by one. But because they are both less than equal to, I can simply drag over these two. So B2, rather I2 and J2 are less than or equal to these two. Okay. And then we still have, well, first of all, my this constraint is wrong because the output constraint, the H is left hand side is greater than equal to, and inadvertently I put it as less than equal to. So change. And here you just select the greater than equal to. Okay. And then I have not yet exhausted. I still have another constraint, which is that the sum of the lambdas, which is in G8 or in G7, is equal to 1. So I have got here, you can actually, before you actually run your program, you go and check this and you find that these are the constraints that you have entered. The sum of the lambdas is equal to 1. The sum of the lambdas is equal to 1. The right hand side of output is, the left hand side is greater than the right hand side, and for the two inputs the left hand side is less than the right hand side, and the lambdas are non-negative, and that is already checked there. And here you select simplex LP. There are 3 options given. We will select simplex LP and then solve. Now, when you solve this, if you get you can get two different kinds of messages. First, that solver found a solution, all constraints are optimally conditioned and satisfied. So this is a valid output. If there was some error, you would get a red exclamation or a warning mark saying that there is something wrong, go and check it. So because it is okay, so you just keep it like that. So what is it telling me? It is telling me that the benchmark will be obtained by a lambda equal to 85.71% times A and 14.28% times B, so they add up to 100%, and the output will be expanded by a factor. The output will be expanded by a factor of 1.457. Actually, what you could do is that if you copy this here, then you see your actual output is 10, your maximum output is 14.57. And so if you want to write your efficiency, that is equal to 1 divided by phi, that's your 6275%. That is your efficiency. So let's recapitulate what we did. We first started with the actual data. Then we created a column of lambda. Then we created a row of the left-hand side variable, the left-hand sides of the constraints, a row for the right-hand side of the constraints. In the right-hand side of the constraints, we entered the actual outputs and inputs, but then we realized that this is true for the two input constraints, but not true for the output constraint. The right-hand side of the output constraint is the actual output multiplied by your phi. So we define this as you can see, 10 times G5, where G, originally our phi was 0, so that's why it was 0. But these didn't change because the right-hand sides of the input constraints are the actuals. We created the last constraint as here we had the sum of the lambdas, and in our Excel, it was sum of the lambdas is equal to 1. And then once we have created the formulas for the left-hand sides and the right-hand sides of the constraints, etc., we went to solver. And in the solver, we first identified in which cell my objective function is. And that is here. You have to be careful about that, because if you casually lay your this thing here, then it thinks that it is in D11, but that's not the case, right? So you have to, that's the reason why I want to color it, so that I want to make sure that it is showing the correct cell. Then I identified whether it's a max problem or a mean problem. Then it wanted to know what are my choice variables. My choice variables are the lambdas and phi, which also happen to be my objective function, but that's not always the case. So I identified the choice variables or the changing variable cells. Then I added the constraints. The constraints are the sum of the lambdas is equal to 1, which is given here in G7, where we have the sum of the lambdas. Then the right-hand side, the left-hand side of the output constraint is greater than the right-hand side, and the left-hand sides of the two input constraints are less than equal to their corresponding right-hand sides. And then this is automatically checked, and unless you have got reasons to, you will just keep it like that, and you will select among the alternative solution procedures the simplex LP, and then you would just run this. So let's do this again. Let me close this and set this to 0 and set this to 0. And because you see now it is saying efficiency is division by 0, because don't ignore it. Don't worry about it, because once we get a value of phi, the efficiency will automatically be counted. Then after doing this, we go to data and solver. And solve. And okay, and this is what you got. Now, today is not, I don't have the time to do it today. Actually, we have very little time. I will probably be able to, in tomorrow's class, I will probably be able to give you more about the input and output oriented efficiency and perhaps a little bit of the scale efficiency. But I won't be able to cover, because I can quickly go over, but that will not make sense. That will be just like reading my book. If you want me to explain to you, I have to go very, very slow. And 4 hours are very, very limited. The first time I taught in Jadavpur University, that was 30 hours. And even then, it was not also possible to cover all of it. So next time I'm going to tell you, do I have to do it for each one of them? Well, in other words, first of all, do I have to enter the actual right-hand sides for each one of them? Because you see that for each problem, the left-hand sides will not change. Only the right-hand sides, this 10, 8, 8 will be replaced by 15, 4, 9 or 12, 5, 2 or 10, 8, 8, etc. So yes, you can write in the index function, which you just simply say the observation number this, and it will automatically pick up the actual output and input and enter them here like the way we do. But even that would be a lot of work, that because I will have to write down each one of them before I move on to the next one. And there is the so-called VBA, the Visual Basic Macro, which will allow you to do all of them through a single macro. And perhaps the best thing to redesign this is to go mainly over the input oriented, output oriented, and show you first how to use the index function and how to use the VBA macro. And with any time left, I will be able to talk about scale efficiency. And I don't know whether that is good for you, because you have to make a choice between actually learning how to do it, whatever little you are learning, or getting a lot of concepts, but not being able to guide it through how to actually do it with your Excel on your laptop. So let me stop here and let me throw it open for any questions that you may have.
Do you have any question?
Okay,
Sir,
to
I
answer
have
your
a question. Sir, I have a
okay,
question.
I see that there was there are questions about DA software. It's up to your choice. I never recommend software, because I do not learn geography by reading timetables. I learn geography by reading geography. And if I write my model, I use my own model, because the software actually assumes what you are going to do. And you will be able to estimate only what they think you are able to do. So I won't recommend any software. It's up to you to decide.
Sir, you have given a data set, no, sir? SEB 2001.
If you have data problem, then don't do data envelopment analysis, because it is your research. It's not a homework. Homework, they give you a data and ask you to estimate. For your research, you have to find the data, you have to ask your question. Otherwise, it's just a homework. I cannot answer your data problems.
Sir, I have a question.
Yeah.
Sir, if I change the farm and want to check the efficiency of A, B, C, A, B, and D, E, then the lambda will change simultaneously. Isn't it, sir? Every time lambda will be different.
Yes, of course. Because for A and B, you are going to see that lambda is 1, all other lambdas are 0. That means that A is efficient. So is it for B. But for D and E, it is going to be different. Yes.
And this efficiency score is for C. Then if I calculate in this way, can we compare the efficiency of ABC as they are having different set of lambdas? Weights are different. Can we compare the efficiency?
Well, you see, let's go back to the slide, okay? Let's go back to the slide. when you are looking at a point like P5 here, when you are looking at point at P5, you are going to go upwards, and that's a point between P1 and P3, right?
Yes.
So that means that it is a weighted average of 1 and 3. When you are looking at a point like P6 and move up, that is somewhere between P3 and P4. So that would mean that that's a weighted average of P3 and P4. So that lambda 3 and lambda 4 will be non-zero, the others would be 0. So essentially what you are really saying is that I have got a point and I have got a frontier which is made up of straight lines, and these straight lines are some facets connecting different pairs of points. And so if this point, the point above P5 is closer to P3 rather than to P1, that means that you are giving more weight to 3 and than to 1. Because if lambda was 1, then P3 would be the observed point. And if lambda was 0, then this would be the observed point. So it depends upon the lambdas tell you whether the point on the P3, P5, P1, P3 segment, is it closer to P1 or is it closer to P3? Similarly, for this point P5 or rather P6, it's a point between P3 and P4. So the lambdas, lambda 1, lambda 2, etc., they are 0. Only lambda 3 and lambda 4 will be relevant. And so essentially those lambdas which are non-zero are really the group you should study, because you are asked to do something which is some mixture of those two firms. You don't worry about others. You don't have to look at everybody. You only look at those firms for whom the lambda is strictly positive, and give more weight to the firm where the lambda is closer to 1, because those firms are more relevant for you than the other firms. Any other question?
Any more questions from anyone sent? Please ask. Sir, I think they need some time to
I'm sure
digest it.
It took me 40 years to get here.
Yes, sir. At least, I mean, in 4 hours, it is really not possible to learn everything about the neoclassical production economy. Sir, thank you so much for your valuable talk and your time. I now request Mr. Kollan to do for the vote of thanks. Mr. Kollan, please.
Thank you so much, Dr. Shravanti Maiti Madam, for giving me this opportunity to deliver the vote of thanks for today's session. Now that we have come to an end of this session, I would like to offer my vote of thanks to our resource person, Dr. Subhas Ray sir, for today's session, for enlightening us with his knowledge and for sharing his valuable inputs about productivity, efficiency, data involvement, and analysis. All the important technical part which he has taught us today will definitely add value to our research work in the long run. I'd also like to extend my gratitude to Dr. Dibojyoti Chaudhary sir, Senior Assistant Professor, Assam University, for organizing such an informative session for all of us. I'd also like to thank all the organizing members from Vidyasagar University and all backend coordinators for their continuous support for making this event successful. Last but not the least, a big thank you to all the participants who are present here today. Without you all, it would not have been possible to make this session a successful one. Now, I'd like to end this session with one quote by Chanakya. One small chain is enough to control a large elephant. A small lamp is enough to erase the darkness. A thunderbolt is enough to crush a mountain. Your body shape, size, beauty are not important. Only your strength and confidence are important. Having said that, I would like to end the session. Till then, stay safe, stay healthy. Shubh Ratri. Thank you. Over to co-convener of the program, Dr. Sharvanti Maiti, madam. Thank you.
Thank you, Kullan, and a great thank you to Professor Subhashi Ray. So thank you. Participants, Professor Ray will take another class on DEA and discuss the other issues related to DEA tomorrow from 6:30 IST. Sir, thank you. Good night. Shivratri to all of you.
Thank you very much. It was a pleasure talking to you. And as you might know that I intend to visit, although for a day or maybe half a day, the university in early January.
January, sir.
And also there will be a 3-day DA workshop, which is being planned at the Birla Institute of Management Technology in Noida. And I will ask the host, Gokul, to send a message to Professor Maiti, and anybody who might be interested might want to consider. Although it is, I think that you will find me rather rude when I say that you ask me for where am I going to find the data, and I respond by saying, how should I know? Because it's your research. But I like giving the bad news first. So if you're looking for data, then look at IndiaStat. Don't look at me. And if you are looking for software, go and get something off the web. Don't ask me, because my approach is, it is my research. I will decide how I will formulate the model, because those who take a model and punch in data in there are probably a dozen a rupee. But those who can create their models are the people who end up being good researchers.
Yes, sir, absolutely correct. And the data is there, software is there. And if we put data, software will give us the answer. Now it is our task to explain it. And today we learn how to explain it. Thank you so much, sir. I feel interested to participate your elaborated program. I hope you will inform me about the program, and I am going to participate it. And I am sure lots of people from here also going to participate it. But I once again take this opportunity to request you in tomorrow's session, please share your Bari poem with us, please, sir.
Which data?
No, data, Bari poem, your poem, Bari, written by you.
You can find that in Deshpatrika.
Yeah, but we want to listen from you. You
Okay,
recite
will
it,
do.
we want to.
Yeah,
Okay.
but is everybody Bengali speaking?
Most of us Bengali speaking, but they will understand. Emotion
No, we can
doesn't,
understand Bengali.
and more of our emotion doesn't need any language, sir.
Okay, I will probably give a translation, because Jayashree Patil Dake, she wanted a translation, so I will give you a translation. Okay, yes. Take care.
Take care, sir. And for you, good morning, and for all of us, good night. Thank you.
Bye.
Bye. All participants are requested to leave the platform one by one. Thank you so much.